Good morning, students. Today we shall be doing electrostatic flux and how do we calculate this electrostatic flux, as well as how the electric field changes as we change my position, all these things. So let's take this point O, where the plus Q charge is placed, and this plus Q charge is generating an electrostatic field. So everyone knows this electrostatic field will be radially outward, it will be radially outward, in this direction. Suppose this is the position vector r, so and this is the point P. So the electrostatic field at point P is 1 by 4 pi epsilon 0 q by r square times r cap. R cap is the unit vector along increase in r. So that means this is the r cap direction and this is the direction of the field. So this electric field will be a vector quantity. Fine. Now if we come here, for example, if we come here, suppose to another position, suppose here, naturally the radius vector will be different. The magnitude of this radius vector will be little less. The angle with respect to x, y, z will also be different, and the P point will also shift to this point, and the unit vector from this point to this point will be in this direction, and naturally the electric field will also be in this direction. So here the electric field E will be here, this point P, suppose this point is P1 and this point is P2 point, so this will be EP1 and this will be EP2, so that will be 1 by 4 pi epsilon 0 q by r square times r cap. See, this r cap changes as we change my position, so it is not a constant vector. The magnitude of r cap is constant, but the direction changes, so r cap is not a constant vector. So let me place the frames that will help you to understand things. So suppose this is one axis, this is the other axis, and this is the other axis, and in our right-handed system this is x, this is y, and this is z, right? Now what is electric flux? Electric flux is defined as the number of lines of force or the amount of lines of force passing through a given area. So let's draw that given area first, that is important. Take this area, any area. What color I shall take? So take this color as green. Suppose this is the area. Suppose this is the area, right? So this is the area and we are interested in the flux passing through this area. So then what you need to do is you need to draw the electric field till here, and take the electric field, that's using the sky color. So the electric field will be suppose from here, from here it will be to this point, right? And the direction will be along this radius vector. So let's draw this electric field. Will be in this direction. Please keep this in mind that as we go radially outward, the electric field decreases. So technically this electric field should be more at P2. So let me correct this. This electric field will be more, the magnitude will be more. So let me increase the arrow a little bit. And suppose if this point on this surface, you got me, this electric field at P2, so electric field at P2 will be greater than electric field at P1. I am talking of the magnitude. And suppose if this point is P3, on the surface, so E P3 vector will be definitely 1 by 4 pi epsilon 0 q by r squared times r cap. But as far as this magnitude is concerned, EP1 EP1 is at the middle, so rather this will be EP2. EP2 is greater than magnitude of EP1 fine, is greater than magnitude of EP3. Why? Since magnitude of R2 is less than magnitude of R1 is less than magnitude of R3. Look at the geometry, right? And this comes in the denominator. Now we are talking of electric flux. Check this green area. What we have to do is we need to find the amount of electric field passing through this area. So what you have to do, take a very small elemental area on this. Take a very small elemental area, let's take it in blue, this small elemental area here, right, this elemental area. Now what's the direction of this area? The magnitude of area is dA, but the area vector will be in this direction, right? This is dA vector. Why this is dA vector? Because the area vector is perpendicular to the area. If you traverse the area in an anti-clockwise fashion, you get your thumb finger will point the direction of the area, and this angle is the angle between the electric field and the area vector A. Let me draw another area, then it will make you understand a little better. Suppose I take an area here. Suppose I take an area here, and whether it's curved or flat, it doesn't matter at all. The thing is, we need to find the electric field at some point. This is the point, and this is the radius vector r, any radius vector r. You need to take the area here, dA. Now depending upon the orientation of the surface, you will get the area vector. Suppose the area vector will be perpendicular to this. Suppose this is the area vector, so let's make it a little shorter. This is the area vector, okay. dA vector. And what's the direction of this electric field? The direction of this electric field will be in this direction, right? Now what's the angle between them? This is the angle, theta. Clear? If you just extrapolate this line, and this is line, the angle between these two is the angle between them. Now if we need to find the flux through this area S, the flux phi is the surface integral of E dot dA for the whole surface. Remember, this is definitely a double integral because it is a surface integral, so make it a double integral for the whole surface, E dot dA, and this will be double integral E dA cos theta on the surface. This is the flux. Now see, as we change position from here to here to here, the direction of the electric field will change and the direction of dA will also change, so theta will also change, right? So as these thing changes, you need to find the value at each point and sum them. Now in this case you have to integrate them because it is varying continuously, right? Now I tell you, these integrations are difficult unless there is a symmetry in the area. Either you are given the area as a spherical area, area of a sphere, or a part of a sphere, or a part of a cylinder, or the equation of the area is given, it's a plane surface given, and you can also find this electric flux by using Gauss theorem without going into the integration. So that will be our next topic. Our next topic will be Gauss theorem. Thank you very much.